Now that we've defined stress as force per unit area and strain as deformation per unit length, we can create something called the stress-strain curve. This curve is unique to each material and doesn't depend on the geometry of the specimen. In the stress-strain curve, stress is normalized per area and strain is normalized per length, which removes the geometric dependence. The generation of a stress-strain curve is done via tensile testing, and you can click on this link to watch a video of a tensile test if you want to see what that looks like. For low-carbon steels, we have the following stress-strain diagram, with stress on the y-axis and strain reported as a percentage on the x-axis. There's some key features of the stress-strain diagram that we'll talk about. The first feature we'll talk about is the yield strength of a material. Yield strength is denoted as sigma y and corresponds to the yield stress of the material. This is the point at which the material will not return to its original shape after the load is removed, and is used as a design point within the system. Below the yield strength, the material behaves linearly. This region is known as the linear elastic region. Linear meaning that the line behaves linearly, and elastic meaning that the material is behaving elastically. Within this region, we can apply a load and then remove that load, and the material will return to its original size and shape. Sigma U is the ultimate yield strength of the material and is the maximum strength that a material can withstand. Note that sigma U exists when there is about a 20% strain within the system. This will result in a major deformation within the system, so we don't ever want to use this as a design point. There are two unique features within the linear region. The first is the proportional limit, which exists below the elastic limit and marks the transition from linear to nonlinear behavior. The proportional limit is going to be very important because below it, we can easily model the behavior of a material because we have a straight line. Beyond there, we don't have an equation to model the behavior of a material and have to rely on the stress-strain curve to determine the deformation versus the applied load. The elastic limit is just above the proportional limit and is the last point at which the material will return to its original condition after loading is removed. If the elastic limit is exceeded, the material will still be deformed after the load is removed. The elastic limit is synonymous with the yield point, which corresponds to the yield stress and yield strength. Beneath the proportional limit, the stress-strain relationship is given by Hooke's law, also known as the modulus of elasticity or Young's modulus. Hooke's law states that the modulus of elasticity, E, is equal to stress per strain, with units of pascals. E is simply the slope of the line in the linear elastic region from the stress-strain diagram. E is a material property that doesn't depend on the size or shape of the material and will differ by material. Similar to the stress-strain diagram, we can have a shear stress-shear strain diagram, which we'll cover shortly. In the shear stress-shear strain diagram, we have G, which is the shear modulus, or modulus of rigidity, and this is equal to the shear stress per shear strain, also with units of pascals. Once again, G is a material property and is not dependent on size or shape. Some common values for elastic and shear modulus are as follows. For structural steel, the elastic modulus is typically on the order of 200 gigapascals, and its shear modulus is typically around 76 gigapascal. For aluminum alloys, the elastic modulus is typically around 73 gigapascals, and the shear modulus is typically around 28 gigapascal. Each material is going to have a unique modulus of elasticity and a unique shear modulus. You have to look this up for the material, for the alloy, as well as for the manufacturing process, as all of these can change the material's properties. As noted, the modulus of elasticity quantifies the resistance of the material to deformation via axial loading. A material with a high modulus of elasticity can withstand a high stress before it deforms. The shear modulus, or modulus of rigidity, is the resistance to shearing. A material with a high modulus of rigidity can withstand a very large shear stress before deforming. Let's take a look at the stress-strain diagram for aluminum alloys. Note that aluminum alloys exhibit a linear elastic region that's below the yield stress. Unlike low-carbon steels, we're not able to see the yielding of the material on the graph. As we go from the yield stress, we increase non-linearly to the ultimate stress, and right after this, the material ruptures. The yield stress for aluminum alloys can be found via the offset method, where we draw a line parallel to the linear elastic region at a 0.2% offset from the origin on the x-axis, as shown below. The average shear strain of an element, gamma average, is equal to the deformation due to the shear per the initial length. If we consider a box pinned at the origin as a node in diagram A with an applied load F, we see that F sub x is going to cause shearing across the top of the box, and F sub y is going to cause shearing across the right face of the box. This will cause a deformation delta with respect to the x and y axes, where the box is going to deform some angle phi. The average shear strain is the delta due to shearing per the initial length. For small angles, this is approximately equal to the tangent of phi. Let's look at an example. We have a rectangular block of material that's bonded to two horizontal rigid plates. The lower plate is fixed to the ground, while the upper plate is subjected to a horizontal force P that's providing shear to the system. Knowing the upper force moves the upper plate 0.04 centimeters and the material has a height of 2 centimeters, we want to determine the average shearing strain, gamma xy, xy being the planes we're looking at. Recall that the average shearing strain is equal to the deformation per the height of the body. So, we're going to take the deformation of 0.04 centimeters per the height of the body, 2 centimeters, which gives us an average shear strain of 0.02. Again, note that this value is dimensionless. If we calculate the angle phi, this is approximately equal to 1.15 degrees.